Hi, everybody, and welcome to today's Seed World Innovation Series webinar brought to you by Computomics. My name is Mark Zinkowitz, and I serve as an editor with Seed World, and today I'm happy to be your host. Today's theme, as you can see on the screen, is precision barley breeding for sustainable, high-quality varieties. Now, we're going to hear from two experts who are going to talk about this topic and how technology is allowing breeders to produce new plant varieties much faster and under less predictable growing conditions. Now, during today's presentation, you'll likely have some questions for our two speakers. Please type these into the chat box at any time during the webinar, and we'll address them during the Q&A session that we'll hold at the end of the webinar. So in other words, you don't have to wait until the end to ask your question. Type it in at any time. Now, this webinar is being recorded and will be made available on demand on our website, seedworld.com, in the coming hours. Now, climate change, loss of genetic diversity, and selection intensity are just a few challenges that breeders are facing these days. As we all know, climate change is strongly impacting the cultivation of malting barley. Breeders face the critical task of developing resilient and high-quality malting barley varieties, while at the same time upholding sustainable practices and building robust supply chains. Now, the brewing industry demands nothing but the best barley for the malting process, with a stable profile, consistent quality, and reliable characteristics. Now, in this context, advanced technology becomes really important in meeting the ambitious requirements of all the stakeholders involved. And that includes sustainability goals, supply chain continuity, and the brewing industry's quality standards. Now, Computomics machine learning technology, xSeedScore, helps to develop novel cultivars with specific trait combinations that are of high value in the malting process. By leveraging environmental data, xSeedScore identifies the best performing crosses based on current and future environmental conditions. Now, during this webinar, you're going to learn about the cultivation of high-quality malting barley varieties while adhering to sustainability and supply chain goals, how machine learning deciphers how interactions between genetics and environments result in a trait's manifestation with pattern recognition, and finally, the benefits and results of using machine learning in plant breeding. Now, today's speakers are Patricia Rica, Product Manager at Computomics, and Austin Case, who works in barley breeding and research at AB InBev, which is the world's largest brewer. Welcome to both of you. How are you today?
I'm good, thank you.
Doing great, thanks.
Great, nice to see you guys. Now, Austin, you're actually going to kick things off today by talking about AB InBev's sustainability and breeding goals. We're then going to move into a discussion of xSeedScore and the tools and technologies to achieve breeders' goals. We're going to discuss the results and effects of using xSeedScore. And finally, we'll do our Q&A at the end of the webinar. So, Austin, I will turn the floor over to you to talk about Anheuser-Busch InBev's sustainability and breeding goals. Austin, if you need anything during the webinar or anything, feel free to call out and I will reappear, but I will disappear for the time being and let you give us some information.
Great. Well, thank you very much. Yeah, happy to be here this morning to talk a little bit about some of the targets we have at Global Barley Research and AB InBev's barley breeding projects. So, why would a really large brewing company be interested in plant breeding? Why would they hire plant breeders, plant geneticists like myself? And a lot of it is related to our commitment to sustainable and high quality barley supply chain to make the best beers that we can. We believe we need to start with the highest quality raw materials. So we have some sustainability goals out there related to 2025 and smart agriculture, being all of the growers that we work with would be skilled, connected, and financially empowered. And how our unit, or the barley breeding teams around the world, are involved is in the skilled aspect of that target, that growers have access to high performing barley varieties that are tailored to their specific growing environment, that have advantageous traits for not only the growers, but then the maltsters and brewers as well. And then there's some amount of crop protocol released with that, or a information about how to best grow that variety, what type of nitrogen, seeding rate, sort of thing that variety would prefer. And if you kind of think about the whole supply chain, this is where it gets really interesting to be a breeder embedded within a large company like AB InBev, is that we get to think about how to breed for not just the farmer or the brewer or the maltster. We get to really think about the entirety of the supply chain, which brings a lot of benefits, and that there's more things to think about. There's more people to interact with, and a lot of challenges in that. Some of these attributes of a barley variety may be really good for one consumer, but a drawback for another consumer. So when we have the benefit that we can think really from seed to sip is what we like to think of when we're looking at our supply chain and how we can impact it with variety development. And so, as I mentioned, I am the global barley breeder for Global Barley Research. So we're based out of Fort Collins, Colorado, which is where I'm at this morning. However, we have breeding sites and breeding locations really throughout the barley growing world. You can see on the left-hand side the different dots are showing different locations where we have either some type of barley breeding team agreement with some of the local zone teams there, or something to do with crops and also alternative crops and barley crop management as well. And it more or less reflects the general areas where barley's grown throughout the world. And not everyone here may be familiar with where your barley necessarily comes from, but obviously Europe, South America, and North America are very big, as well as we're also involved in Africa. In fact, I'm on my way down to South Africa here at the end of the week to meet with our local team there. So all that really provides a really excellent amount of data to think about how we can adapt barley for different regions of the world, and how climate plays an impact on that, which we're going to get into a little bit later in the talk. And then, like I said, if we think about what we're doing and why we're breeding, we have these biggest impacts from our three main consumers. When we think about our Global Barley Research and our biggest consumers, the growers, really thinking about grain yield and grain yield consistency, and that might be a specific trait to malt barley, in that typically it's grown a little bit more as a niche crop, and so growers are maybe not necessarily chasing all-out yield, but consistent yield. That's true for all crops, but I think especially so in barley, which is related to what we're going to talk about later. Kernel plumpness is acceptance rate. If typically in most geographies, malt barley is sold at a premium, and if you don't make the premium grade, then usually it comes with a discount. Disease resistance, pre-harvest sprout tolerance is a big one we'll talk about later. And then all the traits related to malting are mostly about enzymatic formation. If you're familiar with the brewing process, this is where a lot of the enzymes are made that you need in brewing. And then even germination and processing time. And then when we get to the brew house, obviously malt extract, or this is how efficient we can be at actually making making beer out of the malt. Is really important trait for barley varieties, and it differs substantially by variety. And then a lot of things related to sensory profile and beer quality is really important. So these are all really interesting traits that are fun as a breeder to work on, but a lot of them are maybe in repulsion, or they don't segregate together. So we have a lot of choices to be made, and that's where this precision idea comes in, and that we were trying to, how can we be more precise to hit these difficult targets? And one of the ways we're doing that, as we're going to talk about, is accelerating our breeding pipeline. And that is really our journey to a 5-year breeding pipeline. If you look at most small grains breeding pipelines, barley breeding pipelines, they'll be anywhere from 10 to 12 years from cross to maybe commercialization. We're on a road to 5. And part of how we're going to get there is related to some of the technologies we're tapping in today, related to genomic selection, some things about crossing, genomics crossing, and then other high throughput phenotyping traits, purity work we're doing with molecular markers, as well as the climate analysis that we're gonna talk about in a minute. And then this is just a broad overview of all the different breeding programs and what we see going forward. And if you on the left-hand side, you can kind of see the basic breakout between breeding and crop management information that we're working on, as well as the variety pipeline funnel globally on the right-hand side, showing a nice funnel shape there. So as a global breeder responsible for sort of managing all these zones, having an ability to tap into data like this and understand where our breeding programs is really beneficial. And it also presents a really great data set in that we can look at variety performance in different regions of the world. Same variety planted globally can really provide us a lot of information around allele performance and the impact of the environment on barley. So with that, I'm going to switch it over to Patricia, and she's going to talk about their Computomics' xSeedScore and some of the technologies that we've been able to tap into.
Thank you very much, Austin. So now we've heard about Austin's goals and challenges he's currently facing with his breeding program and the global barley breeding programs they have at ABI. And we support them with xSeedScore, which is a tool to achieve his goals and to achieve goals of breeders in general. So first, what's xSeedScore? It's a machine learning-based tool where we use your data to train our xSeedScore models with to predict the unknown. As a training data set, we use the genetic information you have, the phenotyping information you have for these genetics, and some sort of environmental information about where you did these tests. We train our model. It understands the interaction of the genetics with the environment, showing a specific phenotype in this environment. And as soon as these models are trained, we can start predicting, and we can predict for different goals. So one goal could be you have genetics that you can't test everywhere in the field, of course, and in every environment. So we can predict how these genetics would have performed in other environments you did not test them in so far, kind of filling the gaps and increasing your testing data artificially. The second thing we can predict for our new genetics. So they come out of your breeding pipeline, but you did not yet test them in the field. We can simulate and predict how they would perform in the field. And with this information, a breeder can make decisions on if they actually want to spend money on them and test them in the field or not. The third thing, which is the topic of today, is predicting for environments the model did not see and where you did not do any testing so far. That could be some other locations you're interested in, but it also can be future climates. And that's the topic of today, predicting for future climates, which is a very challenging task and not done by many people so far. Now we have trained our models, we have made predictions of the thing you're interested in, And then the breeder actually comes in and starts making selections based on the predictions, either which material do they want to keep, which crosses to make. And with machine learning, the nice thing is that you can very easily integrate very diverse data sets to actually reflect the biological reality as precisely as possible. The absolutely mandatory data set we need for making for training models and for making predictions are phenotype measurements and the correlated phenotype, so the genetic information, so the genetics you tested in the field, and some sort of information about the environments you tested in that could be as little as location identifier and year. However, you can add all these additional data types to machine learning very easily. Some of them describe the environment more precisely, like soil information, weather information, other types of climate data. We can include quantitative data like methylation, transcriptomic data to actually describe what happens in the plants. We can add field management data as a human-made environmental variable, and even microbiome data describing the interaction between the microbiome and your plants in the rhizosphere, for example. And in the future, many more data types are possible to include very easily. So where in a breeding pipeline could xSeedScore be applied? This is an example for variety development because today we're talking about barley, but that's also applicable to hybrid breeding, for example. If you look at a breeding cycle from a bird's eye perspective, it's broken out into 3 different phases. In phase 1, you create the actual variation by making a cross, for example. In phase 2, you're forming the variety and become or get a homozygous new potential variety. And in phase 3, all these potential varieties are tested to find the one that has the best performance, which can then be commercially launched. With xSeedScore, we can help you in phase 1. The thing we can do here is the simulating the crosses that are possible and that you're interested in as a breeder. We simulate the genetics that can come out of a cross, basically simulate phase 2. And as soon as we have potential genetics that could come out of phase 2, we predict how they would perform in the field. With this information, you can, on the one hand, figure out which crosses have the highest potential of success, and on the other hand, which parents are generally good parents, which you can pair with many other parents to make a new cross. We can then also help in phase 3. As soon as your genetics are fixed and they basically come out of phase 2 and are about to enter phase 3, they get sequenced, and we can take the sequencing data and predict how they would perform in the field trials. With that information, you can already discard variety or potential varieties that don't have a high probability of being successful and focus your efforts, your money, space, manpower on the material that has the highest probability of being successful. And with that, you can reach a much higher precision in your breeding program. But now the challenge today is, how can we ensure that with all of these tools, we still have a sustainable and continuous supply chain? As Austin mentioned, that's of a very important to him and to his company in general, and I guess also to everyone facing climate change. And the core question here is basically, how can how will existing and future varieties actually perform under the changing climate conditions? Because especially for barley, it can be in the market for a very long time. So Austin, maybe you want to chip in and explain to us what you've seen so far.
Yeah. So barley is a rather unique crop in that it has varietal integrity preserved at the malt house. So if you're not familiar, maltsters typically malt everything by variety, and then usually by geography or even regional differences by variety will be segregated off, because the malting process can be impacted by that. And so once growers have felt comfortable with a variety, once the maltsters and brewers like a variety, they tend to stay for quite some time. So, 10 plus years is not uncommon. On the left-hand side, you can see just the basic breakout percentage of varietal mix in the U.S. over since 1998 through 2020. This is all varieties reported by USDA data. And you can see they last quite some time. As you move to the right-hand side, we've gotten quicker about turning over varieties and capturing more of that genetic gain. But from a breeder perspective, right, the concern is, if I release this now, is it still going to look good in 10 years? Whereas like with a corn hybrid, maybe you're only really looking for 1-2 years. So barley has some unique characteristics on that side.
Thanks very much for explaining that to us. So as Austin explained, it's super important, especially for barley, to understand if the variety you create now is viable in the future and is still appealing to growers, malt houses, and brewing companies. So our goal in this project was to predict how the varieties he has at hand at the moment will perform under these future climate conditions. Kind of sounds easy. You train a model, you predict how your varieties perform in the future, but the big question is, first, how do we do it? And then the second one is, how precise are we with doing that? And we took several steps in that project. The first one was to actually integrate the climate data we had at hand for the material and the trials Austin worked on so far. So the first step was to supplement the very simple description of the environment of location identifier and year by actually climate and environmental data like soil information and weather data, which was supplemented with crop growth models to ensure that whatever we put into the model as environmental variables is important for barley during its growing season, and that we don't add unimportant information to the model. In addition, we were able to get climate simulations for future climates. They were provided by ABI and created by them. And we went for 2 different climate scenarios. The SSP 245 scenario, which assumes that there is a moderate global cooperation to address climate change. So we know climate change is there, we do a little bit about it, and we have moderate greenhouse gas emissions. The second scenario, the SSP 585 climate model, assumes limited efforts to mitigate climate change. So there are socioeconomic and political choices made that basically result in no big changes from humans to mitigate climate change. And we have a high greenhouse gas emission scenario. We got climate models for 10 years. From 2035 till 2044, and we had 25 models per year and SSP scenario, resulting in 500 different climate models. We went for so many models because we don't want to be precise about how the future will look like in terms of climate. What we want to achieve here is to see if the varieties that are currently worked on in the breeding programs, if they are able to survive and to thrive in many different possible scenarios we will face, because we don't know how the future will look like at the moment. So first we started with assessing the climate data we had at hand to then go into the predictions later on. So here we looked into the available environmental information, weather and soil data in this case, for the trial locations we had at hand, and we assessed the clusters that were forming based on similarity of locations. And we do see that, of course, there are some clusters forming. We know some of them are due to the regions the trials were in, but some of these clusters also inform us about redundant locations or locations which are very differentiating and which could contain a lot of information if you do trials in these 2 locations. In the next step, we included the genetic response to the different environments. So here on the right-hand side, you see a plot where the locations are on the x-axis we plotted the yield we saw in these locations, and the color reflects the year that was the trial happened in. And as expected, you do see that there are some locations which have a really wide range of yield showing. Other locations have a very narrow range of yield, so they are more stable in the yield plants will show in these locations. So we clearly see here the G by E happening basically. Environment has a huge effect, year has a huge effect, and that's something we want to capture here. In a third step, we compared the future climate models to the past, the environments in the past trial locations. Because machine learning still has it's a pretty difficult task for machine learning to extrapolate to something it has not seen. That's like out of the range from what it has seen. So here we have an example where we looked into the heat stress frequency and compared heat stress frequency between past environments in orange and models or climate conditions under the SSP 585 model. And what we do see is that, sure, there are some locations where they differ very much, where the past environments don't have these extreme values that we will see in the future. But when we look overall and look at all the heat stress frequencies from the past years and all the locations, and we compare it to all the heat stress frequency in future environments, we do see there's a huge overlap. And that makes us more confident that we are able to predict for these climate conditions, for the future climate conditions, because we are still in a similar range. So now what's the idea behind all of that? So the idea is, as mentioned before as well, we train with the performance of past environments to predict the performance of varieties in future environments. So we take data from phase 3, from the testing phase. We take all the genetic and phenotypic information, the environmental information we gathered from these trials. We train our machine learning based xSeedScore models with these trial data. And then the goal is to predict the genetics we have at hand in future climates and see how they will perform under future climates. The big question here is, as I've mentioned before, how precisely can we actually predict for these future climates? And generally, how accurately can we predict for environments the model has not seen? Because future climates are also an environment the model has not seen so far. So our approach was first to validate how accurately can we be. And the way we did that was by a leave 1 year out cross-validation. So basically, we took all the training data and we removed a whole year of testing from the training data, trained the model only on the remaining years, and then predicted for the year we left out from training. And with that, you get predictions for something where you have the actually known value for already. And these validations we did for different subsets of data to be sure that how we do it is correct. And then you can start calculating Pearson correlations. So basically, it's a correlation between the actually observed value and the predicted value. And ideally, you would see a perfect diagonal. That's something you will never see in the near future with a prediction. So we assume the diagonal will have a less steep slope. And here on the right side, you see a plot where we made one example. It's for yield. So we left out a whole year of our yield model and then predicted for this year. You see this one had 5 different locations, and each location is a color. So we see how precisely we were able to predict for these different locations. There are some locations where it didn't work very well, like the gray one, where we have a correlation of almost 0. But then there are several locations where we were able to achieve a correlation of 0.3. That's already pretty high, especially considering that this is yield, which is a very complex trait and where you usually get lower accuracies, and considering that these were whole years the model did not see. So we were very thrilled about this initial result already. And if you look at the whole data set, we got a Pearson correlation overall of around 0.9, and within an environment, we could reach correlations of up to 0.3. So that was pretty exciting for us. However, we also wanted to have another way to assess how well we're able to predict. And one important thing for Austin as well was that we are able to predict or to predict the top performers, that he's not missing out on those which perform really well. We gave us a little bit of wiggle room in this analysis and decided we extract the top 10% of the predicted lines and check if they overlap with the top 25% of the observed performance. And in this case, we actually found out that we had a detection rate of up to 90%. So 90% of the lines that were amongst our top 10% performing lines in the prediction were also found in the top performers in the observed phenotyping data. So with this initial analysis, we first assessed past and future environmental information, and we found an upper boundary of performance that we can assume for predicting for unseen environments. So a detection rate of up to 90% and a Pearson correlation within an environment of up to 0.3. So the next step was now the hard task, which is actually predicting for future climates. And this comes with a caveat. One is that we can't assess accuracy in the traditional way. We don't have actual measurements from future climates, so we can't calculate a simple Pearson correlation. And the next challenge is how to then use the information we create by predicting for future climates. And the approach we took here was, again, we trained our xSeedScore models on the performance in the past, and then we now really predicted the performance in the future climates, where we got the models from ABI. And one thing we looked into is the performance stability, and we did the assessment per trial stage. So the trial stage, the line was in the training data at the moment of being used for this training. And on the very right side, we see the past trials for the performance of the lines in past trials for yield in year 2 and year 3 yield trial and in pre-commercial trials. In the middle, we see the performance per trial stage for the SSP245 model, and on the left side, we see the same for the most extreme weather conditions where we had models for. And one thing you see in the past trials is that we do get an increase of yield over the trial stages. That's expected because Austin, of course, selected material that was performing well for the next trial stage. And another thing we observed was that generally yield was predicted to be lower in the under extreme weather conditions, so in SSP 585. However, we could see that the ranking of the lines overall was pretty stable. So that speaks for top performers at the lines that are top performers at the moment will also be most likely the top performing lines in the future. And what we now can actually start is opening the black box, because machine learning actually is interpretable. We can look into how machine learning interprets the interplay between environmental and genetic components, figure out which environmental components were important for its decision, which genetic components were important, and how which genetics actually respond positively and negatively to environmental components. So with all the models we trained and all the predictions we made, we can now understand what performs well, where, and why to supplement Austin's decisions on what to keep, what to discard to ensure that whatever he gets in the end is sustainable for the future. So concluding this part, we found out that we're able to predict for unseen environments with a very high accuracy. We saw that the ranking of the performance of lines was not strongly affected under future climate conditions. So we see that their performance is stable. And we can now start to understand the interplay between environments and genetics to help Austin and other breeders to face future climate challenges and have a sustainable and continuous supply chain. And with that, I hand over to Austin to talk about results and effects he saw with using xSeedScore so far.
Yeah, that's great. Thanks, Patricia. We the future climate modeling was really an excellent work that we did, because the breeder is always faced with this question of am I making the right decisions, right? That's the question that keeps us all up at night. And is what I'm selecting now going to really work in the future? So that's one part of the breeding program. We'll call that the 10 plus year horizon, right? Looking at the 10 plus year horizon. But what happens when you want to look at the more immediate horizon, like the 2, 3, 4 year horizon? What is some of the effects we've seen in the pipeline, and are things actually going to work well now and in the future? And some of the modeling suggests that it will. So also, using some of the technology, we were hoping to challenge some of the traditional understanding of barley breeding, right? So and some of the linkage of traits that we know about. So in general, if you look throughout the history of kind of variety development in barley, typically high lines with high pre-harvest sprout tolerance. So if you think about in a malt house, right, barley that's high quality, right, so it malts well, is going to be very vigorous when germinating. And if it's very vigorous when germinating, it can perhaps do that in the field before the time is ready for harvest. So which presents problems down the supply chain. It can die in storage if it's started to sprout already. So breeding lines with high levels of pre-harvest sprout tolerance is really important, but typically sprout tolerant lines have high beta-glucan, which is a negative in malting and brewing, and then typically lower diastatic power. So depending upon the type of beer you want to brew, that's usually a negative. High glucan is always a negative. Diastatic power being lower is not always a negative, but typically higher DP is good. And then also maturity time. So as we've kind of thought about climate change and adapting barley for the future, generally lines that are later maturing will have more yield potential, but later maturing lines aren't necessarily the most beneficial if you're dealing with end of the season heat or potential other issues as the climate kind of becomes a little more unstable, or we kind of look at different regions that aren't as amenable to later maturing varieties. So we were wanting to see if we could move the traits in the right direction, so increase yield while decreasing maturity time, and then maintain quality while increasing pre-harvest sprout tolerance. So here's a couple of the results we've seen from using more of these precision breeding type techniques. So on the left-hand side graph, you can see the frequency of varieties coming through the pipeline in one specific pipeline from 2014. So we call that the breeding class to 2022. And then in blue was our basic phenotypic selection pipeline, where we weren't making a whole lot of gain because of the impact between pre-harvest sprout tolerance and quality. We started into some initial journeys around GBLUP, essential regular genomic selection, and we saw some response there, but still quite a bit of an impact from quality side. And then as we started moving into some of the machine learning models, adding some cross predictions, that kind of thing, is we really started seeing acceleration of that pipeline pick up some sprout tolerance while maintaining some varietal performance in quality, and that's what you see on the right hand side. So if we're looking at average beta glucan levels in one specific pipeline here, in the sort of traditional breeding techniques, typically our susceptible lines would have much lower beta glucan, but would be susceptible, and tolerant lines would have high beta glucan. Now we see almost equivalent beta glucan levels on average between our susceptible and our sprout tolerant varieties coming through the pipeline. And then also related to grain yield and maturity. So in the same pipeline where we're really pushing for earlier maturity due to concerns around late season heat and other things, you can see that we've started to gain grain yield as compared to the common check. You can see on the left-hand side there, while also pushing maturity time earlier and earlier. So starting to get at some of those traits that have been difficult to deal with in repulsion and move them in the direction that we prefer, sort of all at once.
Okay, so you've seen that the relationship with ABI developed quite a bit. As Austin just showed, we applied more and more techniques in his breeding program. So just to show you how that developed, we started out in 2020 with a pilot project and got the partnership started. In 2021, we then started with routine predictions where we predicted the performance of lines entering testing phase. So if you remember the 3 phases, after forming the new varieties in phase 2, we predicted how they would perform in the field so that Austin could focus his efforts on those with a high probability of being successful with a high precision. In last year then, in 2022, we also added the offspring performance prediction. So predicting which crosses have the highest potential of being successful before even making them. And we did this project on future climate predictions last year as well. For next year, we plan to onboard additional breeding programs. As you've seen in the first part of Austin, they are working in many different regions in the world. So we want to branch out or include those in the predictions as well. And if you think you want to apply xSeedScore in your breeding program as well, there's a certain way how we interact with our customers and how we get them on board. So first we define the goals you have as a breeder. We evaluate the data you have at hand, go into a workshop together to define the optimal setup, maybe figuring out if there's some additional data that could be beneficial. How can xSeedScore be applied to be most effective in your breeding program? And then we actually go into the setup, setting up xSeedScore for specifically your program and apply it routinely.
Thank you so much, Austin and Patrizia, for your presentations. That was terrific, and it shows us just how xSeedScore works in the real world and how powerful a tool it can be in helping breeders and people like Austin to really solve some of these challenges that they are facing. We have some time for a quick Q&A session now. Before we log off for the day. Again, if you have a question, just type it into the chat box. We've had some great conversation going on. Thank you, Austin. I see you've been answering some questions in the chat box while Patrizia has been speaking. Thank you so much for that. I just want to start off. There was a question regarding climate change, Austin, and what AB InBev is doing on breeding for climate resilience, water efficiency. I know you discussed a little bit of that briefly in the chat. Can you just kind of give us, the 411? I mean, climate change is it's in the headlines every day. We're all talking about it. And can you talk a little bit about what you guys are doing in that department?
Yeah, so that's one of the big projects we've been working on lately, involving Computomics, is understanding how climate might impact it. And the other, maybe more basic question is going after what are those environmental stability pieces, so sprout tolerance, and putting it into probably locations where you wouldn't think you need it, right? So in regions where it doesn't really rain too much at harvest, we don't really need sprout tolerance. We've seen massive rain events happen. So I think a lot of it's about throwing out the assumptions of what you think you can and can't get away with, and just assuming that you need to really prepare your breeding pipeline for every eventuality. And the other thing we've been investing a lot into is data systems. Really, you can't get at environmental stability if you don't have really good data systems. And we've been building out global data systems to collect barley phenotypes around the world. So that's one of the main drivers that I think, being a really large company, we can look at performance in the U.S. and in Mexico, and then try to understand how that's going to play long term.
Yeah, it's definitely a long-term endeavor, that's for sure. Patrizia, there was a question here you may be able to help shed some light on in regards to how the xSeedScore's performance, how is xSeedScore's performance in comparison to the common reference prediction models? And secondly, could you also review again how you measure your model performance if the test set is derived from future climate data? Can you talk a little bit about that?
So first, direct comparisons with, I assume GBLUP and BLUP analysis are meant here. So one thing is we often do see that the accuracy is higher, but that really depends on the data set, and also something about machine learning. It comes with a lot of additional benefits, like you can actually understand what's happening in the model. Why does it make certain decisions? What, for example, which environmental components are important for the decision of machine learning, and in turn for the plant to thrive in an environment or not. These are informations you can't really gather from BLUP analysis. Like, there's a lot of additional benefits when you're using machine learning. And then what was the second question again?
So the second part was, can you review again how you measure your model performance if the test set is derived from future climate data?
Okay, so the test set is always from past years. You don't mean the training data set. So the test set, if we predict for the future, basically. Calculating precision is not possible because we don't have real world values to compare to. So what we do is, first we compare it to the actual performance the lines showed in the past. And if you see that there's an inversion of performance, like there is something that was good in the past and becomes really bad in the future, potentially, that could be something where the breeder then can be like, oh, I'm probably a bit more cautious about this variety. But if there is something that's consistent in its performance, it's predicted to be good it was good in the past and it's predicted to be good in the future, then this adds just another level of confidence for the breeder to be like, okay, I go with this variety. It could be still performing really well even under future climate conditions, and could be one of these varieties that's probably in the market for 20 years and having a 50% market share, or what we've seen in the visualization Austin was showing us.
Austin, I'm going to throw the ball back to you here for a second. There was just a question about the crossing of the 2-row and the 6-row barley, and if you could kind of expand on that a little bit. That was really neat. Can you talk a little bit about that endeavor? And
sure.
That's something that you don't hear about every day.
Well, yeah. So I don't know how many of the attendees are, very, very familiar with barley itself, but barley has two basic spike types, grain types, 6-row and 2-row, and it's one gene that controls the row type. Basically, whether you have two rows of flowers or 6 rows of flowers. And historically, 6 rows and 2 rows kind of occupied different environmental niches, not due to anything really related to the spike type necessarily, but I think just due to the breeding history. I'll take the U.S. as an example. 6-row barley predominated in the upper Midwest area. I think just because the early varieties that they imported there from China mostly were well adapted to hot, humid summers, right? Now, as a lot of the industry has moved primarily to 2-row due to some benefits in the malting and brewing process, some breeders have been challenged with trying to adapt 2-row to regions where 6-row typically was the predominant row type. So you can make direct crosses. It's one gene that controls the number of florets that are fertile. What we have seen when I've done it in the past and at University of Minnesota, where I was a PhD student, you can do a lot of 2x6-row crosses, but the yield components tend not to be equivalent. So how a 6-row builds yield tends to not be the same way how a 2-row builds yield. And so I haven't seen a lot of success of a commercialization of a 2x6-row cross. That doesn't say that you can't bring DNA and alleles from one pool to the other. We have successfully done that, but it tends to be more of a long-term effort. So it's kind of one of those enigmas in barley breeding community of, why can't I just make my high-performing 6-row into a 2-row? And I could make essentially a isogenic line and make it a 2-row, but it tends not to perform the same. It's one of those sort of unknown things. But when we look at barley genetics, you can see there's not a lot of cross. They tend to be pretty separate. Breeders keep them separate.
Yeah, it's difficult. You change one thing and then you end up, unintentionally changing a different thing. And so it's definitely not simple when it comes to crossing these plants. Before we sign off for the day, Patricia, I had a question regarding, you talked a lot about data, both quality of data and the amount of data. Which of those enabled you to make this a successful project? Quality, amount, sort of a combination of the two? Can you talk a little bit about that?
So definitely a combination of both, but especially here, as Austin also mentioned, that ABI is a very data like they have a lot of affinity to data and they collect a lot of data. And in this project, we had years and years of testing and trial data available. And that was really what enabled us to predict for future climates, because we had data for a vast amount of years. And usually the year is the thing that has the most extreme effect when you look at environmental components. And that was really the big thing, like the vast amount of data. And generally, machine learning can tolerate quite some amount of noise in the data. But that's, of course, like the more data you have, the more noise it can handle. So it's really a combination. You also need high quality data, which we also had here, but also the vast amount of data was really what enabled us to do this specific project here.
The questions keep coming. We have another minute here, so I'm just going to mention one thing. Scab resistance. Austin, I see you just answered the question in the chat. What progress has been made in scab resistance? Can you touch on that briefly?
Yeah, like I just said, like I just chatted back, not enough. We're getting better. I would say, if you kind of look historically, the newer lines are better than the older lines, but there isn't been enough progress made in barley. In wheat, they seem to have been able to get better resistance faster. In barley, I like to tell everyone, there's not any resistance to scab. There's susceptible, and then there's less susceptible, right? But I would say in general we've been improving, and I think that's one of the pieces that I'm really excited that ABI can work on is we can provide the barley, which is say the 50%. And then we have a whole agronomy team and a crop management advice team that is there to help provide the other 50%. And that's what we've seen is that really you kind of takes, good crop management and, better genetics. But one without the other isn't enough.
Hybrid prediction. How does xSeedScore perform with hybrid prediction? Patricia, do you have any insights on that?
Yeah, so basically the accuracy and precision variety input is just a bit different.
Sorry.
As for barley,
Patricia, you froze up there for 1 second. Can you just repeat from the start?
Yeah, sure. So basically the precision is very similar. The difference here is the input we give to train the models. In the case of barley breeding, the input is the genetics of the variety itself and its performance, and then we can predict for other genetics, for example. In hybrid breeding, we use the genetics of the parents. We simulate the hybrid genetics because that's very defined how the hybrid looks like, and then we predict the performance of the hybrid. And the accuracy is very similar. We don't have a drop in accuracy or a dramatic increase compared to variety development programs. And it's also not easy to compare it because the amount of data you have is very different. The areas that are tested in are very different. So yeah, but just because hybrid versus variety, that's not what's affecting accuracy here.
Great. Well, thank you, Austin. Thank you, Patricia, for the presentation today and for the information. That was wonderful. And that's actually all the time we have today. So again, I want to thank you, Austin and Patricia, for your time, and thank our audience for joining us. Computomics is actually going on tour. You have the opportunity to meet Computomics staff at the EuroSeeds Congress in Malta, which takes place 15 to 18 October 2023. You can also meet Computomics staff at the American Seed Trade Association's Field Crop Seed Convention in Orlando, Florida. That's from 5 to 8 December 2023. For more information, you can email info@computomics.com. And again, I just want to thank Austin and Patricia again for your time today, and thank Computomics for partnering with us on today's Seed World webinar. Again, for more information about xSeedScore and Computomics, please visit Computomics.com. Again, this webinar was recorded and will be available on demand at seedworld.com in the coming days. Thanks, Austin and Patricia. Have a great day.
Thanks for having us.
Thank you to our audience. This is Mark Zinkowitz signing off.